Right now, at this exact moment, a wall of superheated plasma is traveling towards you at approximately 1.5 million kilometers per hour. It left the surface of the Sun some hours ago, hurtling through the 150 million kilometers of empty space between our star and the planet where you are sitting. It carries a magnetic field. And whether that magnetic field is oriented north or south when it arrives, a detail that cannot be confirmed until approximately 15 to 30 minutes before impact, will determine whether the lights stay on in your city, whether the satellites overhead stay in orbit, whether the digital infrastructure holding together the entire modern economy of civilization survives contact, or whether it does not. But that is not even the real story. The real story is not about this event in isolation. The real story is about what the Sun has been doing in 2026, what Solar Cycle 25 has been building toward for years, and what a genuine X-class solar flare striking Earth at full direct impact would mean for a civilization that has wired itself so deeply into electricity, so completely into satellite navigation, so totally into microchip-dependent communication that the entire nervous system of human society now runs through infrastructure that, according to the National Academy of Sciences, a Carrington-level geomagnetic storm could destroy across a significant portion of the northern hemisphere within minutes. Not damage, destroy. With a recovery timeline measured not in days or weeks, but in months and years. And the question is not whether a storm of that magnitude can happen. It already happened once. The evidence is still sitting in Antarctic ice cores. The real question, the one that every solar physicist at NOAA's Space Weather Prediction Center, every satellite operator at the European Space Agency, every grid protection engineer in North America carries with them to bed each night, is what we have actually built to stop it. And what the answer to that question reveals is genuinely alarming. Here's what an X-class solar flare actually is, because the word flare sounds benign. Sounds like a signal flare, like a road hazard, like something you acknowledge and drive past. An X-class solar flare is a detonation on the surface of a star. The Sun's magnetic field in regions called active sunspot zones becomes so twisted and complex that it reaches a critical threshold and then snaps, reconnects, releasing stored electromagnetic energy in a burst of extreme ultraviolet light and X-rays that travels outward at the speed of light. That burst reaches Earth in 8 minutes. 8 minutes is not a warning. 8 minutes is the arrival of the radiation. The X-rays ionize Earth's upper atmosphere, the ionosphere, the layer that shortwave radio signals bounce off of to travel across continents. And they disrupt it. They degrade it. High-frequency radio communications begin to fail. Aviation communications go dark over entire hemispheres. Ships lose contact. This is the radio blackout phase. It lasts minutes to hours, and it happens before the worst arrives. What arrives days later, or in extraordinary storms within hours, is the coronal mass ejection, the CME. 1 billion tons of plasma. 1 billion tons. Which is a number so large that the human mind cannot hold it. A number that makes every ocean on Earth look manageable by comparison. Launched from the solar surface at speeds that in the Carrington event of 1859 reached approximately 2,400 kilometers per second. The CME that struck Earth on September 2, 1859 made the journey from Sun to Earth in just 17.6 hours. Typical CMEs take 2 to 3 days. This one arrived in 17.6 hours because a prior CME had already swept the path clear of ambient solar wind, reducing resistance. A perfect sequence, a cosmic alignment of catastrophic convenience. What happened on September 1st and 2, 1859 was recorded by British astronomer Richard Carrington from his private observatory near London. He was studying a cluster of sunspots through dark filters. When he observed what he described as a sudden flash of intense white light, he sketched it. He noted the time. He did not know what he was looking at. He had just become the first human being to witness a solar flare with his naked eyes, an event so powerful it was bright enough to be visible in broad daylight against the disk of the sun itself. 17 hours later, auroras erupted across the entire planet. People in the northeastern United States read newspapers by the light of the northern lights. Gold miners in the Colorado Rockies woke up at 1 in the morning, lit their campfires, and began cooking breakfast because the sky was so bright they assumed the sun had risen. Auroras blazed across the Caribbean, across Mexico, across Cuba, across the tropics, where no person alive had ever seen the aurora borealis before. And then the telegraph networks of the world went insane. Sparks shot from telegraph machines, papers ignited, operators received electric shocks. Across Europe and North America, the system that was the Internet of 1859, the entire communication backbone of modern civilization at that moment in history, was overwhelmed by geomagnetically induced currents far beyond anything its engineers had ever imagined. Some lines carried enough current that operators disconnected their power supplies entirely and still sent messages, powered solely by the electrical storm in Earth's magnetic field. That was 1859, the year the Carrington event happened. The most powerful geomagnetic storm in recorded human history, and research into Antarctic and Greenland ice cores has confirmed it was not merely the strongest storm of the last century. It was at least twice as powerful as any other geomagnetic storm in the last 500 years. The only question history now asks is, what would the same event look like today? The National Academy of Sciences has answered that question. Their 2008 report and subsequent analyses by Lloyds of London, the Oak Ridge National Laboratory, and solar scientist Pete Riley at Predictive Science Inc. arrived at the same territory from different directions. A Carrington-level geomagnetic storm striking Earth today would expose between 20 and 40 million Americans alone to extended power outages. Not for 9 hours as in the March 1989 Quebec blackout, when a geomagnetic storm one-third the power of Carrington collapsed the Hydro-Quebec grid in under 90 seconds and left 6 million people without electricity. Extended. The National Academy report specifies durations of 16 days to 1 to 2 years depending on transformer availability. The total economic cost in the United States alone, between $600 billion and $2.6 trillion in the first year, 1 to 2 years of recovery, during which hospitals run on generators until the generators run out of fuel, during which water treatment plants, which require continuous electrical operation, begin to fail, during which perishable food and medications are lost within 12 to 24 hours, during which the GPS constellation, the 31 satellites currently orbiting at 20,200 kilometers altitude, the constellation that every smartphone, every cargo ship, every commercial aircraft, every precision agricultural machine on Earth depends on, becomes unreliable or worse. European Space Agency simulations published in late 2025 went further. Research led by spacecraft operations expert Gustavo Baldo Carvalho confirmed that a true Carrington-level event could produce radiation and induced current conditions capable of damaging every satellite in Earth orbit, every satellite. The ESA's Space Weather Modeling Coordinator Jorge Amaya stated it directly. A storm of that magnitude may cause damage to all satellites in orbit. Not some. All. ESA's parallel researcher Carvalho summarized what the scientific consensus has arrived at. This is not a question of whether, it is a question of when. And the when is not as distant as comfortable thinking would prefer. Pete Riley's calculation, published in peer-reviewed literature, put the probability of a Carrington-level or stronger event hitting Earth in any given 10-year window at 12%. 12%. In the decade you are living right now. Those are not astronomical odds. Those are the same odds as a number of risks humanity treats as serious planning priorities. And the return period for an extreme geomagnetic storm, based on historical auroral records, is estimated at 100 to 250 years. The Carrington event was 167 years ago. Now understand what Solar Cycle 25 has been doing in 2026 specifically, because this is where the story stops being theoretical and becomes immediately physically real. Solar Cycle 25 reached its peak sunspot number in August 2024, with a monthly count of 216, the highest peak of the current cycle. The sun was supposed to be winding down from that peak by early 2026. Supposed to be. Instead, in February 2026, a sunspot region designated AR4366 emerged on the solar disk and rapidly grew to roughly half the size of the sunspot that caused the 1859 Carrington event, half the size of the sunspot that produced the most powerful geomagnetic storm in 500 years of recorded history. In a single 24-hour period beginning on February 1, 2026, AR4366 produced more than 18 M-class flares, the second strongest category, and at least 4 X-class flares, including an X8.3 eruption that ranked as the strongest solar flare of 2026 and placed in the top 20 most powerful flares recorded since 1996. Spaceweather.com described the region using 2 words that should not be reassuring: solar flare factory. The flurry of activity confirmed what solar physicists had been watching with concern. Solar cycle 25 had peaked, yes, but a declining cycle is not a quiet cycle, and the magnetic complexity of AR4366, rated beta-gamma delta, the most explosive configuration a sunspot region can carry, meant it was generating multiple events in sequence, each one potentially clearing the path for the next, exactly as happened in September 1859 before the Carrington event itself arrived. The CME from the X8.1 flare on February 1, 2026 struck Earth with a glancing blow on February 5th. It produced G1 geomagnetic storm conditions in the lowest level on the 5-point scale. Auroras were visible at high latitudes. Minor satellite operational impacts were noted. Power grid effects were minimal. The flare factory had fired its most powerful shot of the year, and Earth survived it because the magnetic field of the arriving CME was oriented northward, not southward. It bounced. It coupled poorly with Earth's magnetosphere. The energy stayed largely outside. And that is the margin that separates a headline aurora story from a global catastrophe. One piece of information about the magnetic field orientation of the incoming plasma. One number, the B's component, whether it is positive or negative at the moment of contact. And that number cannot be known until the ACE spacecraft or the DSCOVR satellite at the L1 Lagrange point, approximately 1.5 million kilometers toward the Sun, detects it. At that point, the CME is 15 to 30 minutes away. That is the warning time. That is the window. For the March 1989 storm that blacked out Quebec, the warning was almost nothing. The grid went from normal operation to complete collapse in 90 seconds. Consider the town of Longueuil, Quebec on March 13, 1989. Population at the time, roughly 130,000 people. Ordinary Monday morning. The high-voltage transmission lines that served the province were carrying normal load. At 2:44 in the morning, geomagnetically induced currents, electrical flows generated by the distortion of Earth's magnetic field, flowing silently through the ground, entering the grid through substations, building in the transformer windings, exceeded the tolerance of the system. The first alarm, then the cascade. Within 90 seconds, 6 million people had no power. The blackout lasted 9 hours for most, longer for others. A transformer in Salem, New Jersey was damaged. The economic cost in 1989, Canadian dollars, hundreds of millions. And that storm was rated at roughly G4 on a scale where Carrington would have been a G5 or higher, one category lower than the maximum, 3 times weaker by some measures than what happened in 1859. Now add a critical factor that did not exist in 1989 and barely existed in 2003 during the Halloween solar storms, the modern satellite constellation, the GPS system, the communication satellites, the weather monitoring platforms, the financial transaction satellites, the remote sensing arrays. In 1989, there were roughly 300 operational satellites in Earth orbit. Today, there are more than 9,000. Starlink alone operates over 6,000 satellites in low Earth orbit. An extreme geomagnetic storm does not merely threaten ground infrastructure. It expands the atmosphere. Solar heating causes the upper atmosphere to swell, increasing drag on low Earth orbit satellites, accelerating their orbital decay, pulling them toward re-entry. In smaller events, satellites maneuver to compensate. In a Carrington-class event, the simultaneous maneuvering of thousands of satellites during a period of degraded communications and disrupted ground station operations is not a solved problem. The ESA simulations published in late 2025 were explicit. No satellite's safety would be fully guaranteed. The phrase used in the published findings was not softened by institutional caution. The immense flow of energy ejected by the sun may cause damage to all our satellites in orbit. Think about the people of Reykjavik, Iceland. Population 140,000 in a city built at 64 degrees north latitude, directly in the zone where geomagnetically induced currents in the ground are strongest during major storms. The bedrock beneath Reykjavik is ancient crystalline igneous material, which conducts geomagnetically induced currents far more efficiently than sedimentary rock. During the 1989 Quebec storm, the damaged transformer was in New Jersey, not in Quebec, because the induced currents followed the most conductive pathways in the ground geology. Iceland sits on a mid-ocean ridge, on some of the most electrically conductive geology on the planet in the direct path of the strongest geomagnetic effects. What would the people of Reykjavik ask if they understood that the transformer serving their city has a lead time of 5 months minimum if ordered from scratch, and that only a small number of the largest high-voltage transformers are manufactured globally each year? What would they want to know about the satellites carrying the emergency communication systems, the cardiac monitors relying on GPS-synchronized timestamps, the insulin cold chains, the water pumping stations, the hospital backup generators with their 72-hour fuel supplies? Would they feel protected? Would they feel warned? Now travel to the surface of the sun itself, at least in your mind, because what is happening there is worth understanding in its full scale. A solar flare releases energy equivalent to tens of millions of 100-megaton hydrogen bombs detonated simultaneously. The X8.3 eruption from AR4366 on February 1, 2026, released a surge of extreme ultraviolet radiation and X-rays that ionized Earth's upper atmosphere and caused R3 radio blackouts, the third level on a 5-point scale, disrupting high-frequency communications across the South Pacific, shortwave radio in eastern Australia and New Zealand, and aviation contact across the sunlit hemisphere. A single X-class flare. And the sun produced 4 of them in 24 hours from a single region, with 18 additional M-class events filling the gaps. The region was still growing, still rotating toward a more Earth-directed position as the solar disk turned. Solar physicist Tamitha Skov, commenting on the activity in early 2026, captured what every space weather expert is carrying right now in precisely chosen words. We need to pay attention to radio bursts now. The historical record is not quiet on this subject. The Carrington event of 1859 left its signature not only in newspapers and telegraphs, but in the chemistry of polar ice. When a massive solar eruption injects sulfur dioxide and other reactive particles into Earth's upper atmosphere, those particles settle into polar ice cores over years. Analysis of Greenland and Antarctic ice cores has confirmed the 1859 event as the strongest geomagnetic disturbance in at least 500 years, twice the intensity of anything else in the record. But researchers have found traces of even more extreme events in ice cores dating back thousands of years. The Miyake events, sudden sharp increases in radiocarbon preserved in tree rings, record solar particle events in 774 CE and 993 CE that appear to have been even more energetic than Carrington. The Sun has done this before, not once, multiple times in the geological and isotopic record. The system has the capacity. It has demonstrated the capacity. The question is not whether the capacity exists. The capacity is documented in the ice. And this connects to a second system, because nothing on this planet operates in isolation, and certainly nothing connected to the sun does. The sun's activity cycle does not merely influence space weather. It permeates the entire Earth system in ways that are still being mapped. The TROPOMI and OMI satellite instruments that track volcanic sulfur dioxide, the same instruments that monitor Popocatépetl's gas plumes in central Mexico, the same instruments tracking volcanic unrest globally, also measure the chemistry of the stratosphere as it responds to solar ultraviolet output. The ionosphere that the X-ray pulse disrupts is the same atmospheric layer that reflects radio signals and modulates GPS accuracy. The geomagnetically induced currents that flow through power grids also flow through long oil and gas pipelines, accelerating internal corrosion at rates that pipeline engineers must account for during active solar periods. The radiation belts, the Van Allen belts, which swell and intensify during geomagnetic storms, trap high-energy particles, and then release them in ways that threaten satellites over weeks and months after the primary event. Earth is a system. The sun is a driver of that system. An X-class flare is not a localized event in space. It is a forcing mechanism applied to the entire interconnected network of the planet's electromagnetic environment. Here is what the data actually shows about the current moment. As of April 8, 2026, space weather conditions are in a transitional quiet phase. The KP index, the global measure of geomagnetic activity from 0 to 9, where 5 means storm conditions, is running at 1 to 2. The solar wind is near background levels. The Earth-facing solar disk carries 7 numbered active regions, none currently in the most explosive magnetic configuration. The March 2026 monthly sunspot number came in at 85.9, an uptick from February's 78.2. The 10.7 centimeter radio flux, a proxy for solar activity, reads 118 solar flux units. AR4409, the most recently active region, produced M-class flares as recently as April 4, triggering R1 radio blackouts. Solar activity is forecast to be low to moderate today, April 8th. A 10% chance of X-class flares remains. No Earth-directed CMEs are currently confirmed. This is the quiet between the events. Scientists are careful to say, but that careful language carries its own warning, that quiet periods in a still active solar cycle are not indicators of what the next sunspot region arriving over the solar limb will carry. AR4366 emerged in February 2026 and produced an X8.3 in 24 hours. It appeared without precedent in the weeks before it. New active regions rotate into view from the far side of the sun, where they cannot be directly imaged from Earth, and what they are carrying in terms of magnetic complexity is inferred from helioseismic modeling, measurements of solar sound waves propagating through the solar interior, which provides probabilistic estimates, not certainties. The DSCO VR satellite at L1, which is the frontline early warning system for incoming CMEs, is the primary instrument standing between a surprise extreme space weather event and the global power grid. Its operational status is a matter of genuine, active scientific concern that the space weather community has raised repeatedly in the literature. Think about what the first 12 hours of a direct Carrington-level hit would look like. At 8 minutes, the X-ray burst arrives. Global HF radio disruptions begin. Aviation loses over-the-horizon communication on the sunlit hemisphere. Ships at sea lose contact. This is normal for a major X-flare. Disruptive but manageable. At 15 to 30 minutes before CME impact, the Descover satellite measures the BZ component. If it reads strongly negative, southward orientation, grid operators globally receive alerts. NOAA's Space Weather Prediction Center broadcasts warnings. The time to respond is 15 to 30 minutes. Power grid operators in the most vulnerable zones, the high-latitude regions of Canada, Scandinavia, the northern United States, have 15 to 30 minutes to reduce load, to protect transformers, to prepare for induced current surges. 15 minutes. The research confirms that the magnetic field orientation, the most important single variable in determining Earth impact, can only be measured at L1 with that lead time. Not hours, not days, minutes. At impact, the geomagnetic storm begins. KP rises toward 8-9. Geomagnetically induced currents of potentially more than 100 amperes begin flowing through grid infrastructure. Transformers, the massive, custom-built high-voltage transformers that can weigh up to 300 tons and serve populations of millions, begin experiencing thermal stress from currents flowing through their neutral grounding points. A transformer damaged by geomagnetically induced currents does not trip offline and reset. It saturates, it overheats, it can be destroyed, and a destroyed high-voltage transformer cannot be replaced in days. It cannot be replaced in weeks. The lead time to manufacture a new one is 5 months minimum. The supply chain is global and thin. The human face of this scenario is not abstract. It is the intensive care unit in Halifax, Nova Scotia, where backup generators are rated for 72 hours. It is the dialysis center in Tromsø, Norway, where 3 sessions per week mean the difference between life and death for 200 patients. It is the refrigerated insulin supply for 537 million diabetics worldwide, a supply chain that depends on continuous cold chain management, that depends on reliable power, that depends on the grid staying on. It is the 40 million Americans in the extended outage risk zone identified in the National Academy of Sciences report. Not 40 million who would be inconvenienced, but 40 million whose medical devices, whose water supply, whose heating in winter, whose food preservation would all begin failing within 12 to 24 hours of grid collapse. The loss of electricity would ripple across the social infrastructure, the National Academy wrote, with water distribution affected within several hours, perishable foods and medications lost in 12 to 24 hours, loss of heating and air conditioning, sewage disposal, phone service, fuel resupply, and an eventual loss of clean water resources, requiring dependence on a dangerously dysfunctional transportation system for food and supplies. This is not a description of a natural disaster. This is a description of a civilization systematically failing from the top down. And here's the connection to the second system, the one that shows how the sun and the ground beneath our feet are never as separate as they appear. The trans-Mexican volcanic belt, the tectonic subduction zone where the Cocos Plate dives beneath North America at 6 to 7 centimeters per year, the seismically active fault networks that underlie Japan and Indonesia and the Pacific Northwest, these geological systems are not directly driven by the sun, but they share the same planet, the same ionosphere, the same atmospheric coupling, and research published in multiple journals has documented correlations between periods of intense solar activity and increased seismic and volcanic restlessness, correlations that remain scientifically contested, that carry no consensus, but that appear in datasets across decades. What is not contested is this: a civilization hit by a Carrington-level geomagnetic storm loses the early warning systems that the modern world has built against earthquakes and volcanic eruptions simultaneously. The GPS networks that enable precise ground deformation monitoring around active volcanoes, the same geodetic networks watching the flanks of Popocatépetl, watching the Yellowstone caldera, watching the Cascadia subduction zone, rely on satellites. They rely on GPS signal integrity. They rely on the infrastructure that a G5 geomagnetic storm would compromise or destroy. In the first hours of a global infrastructure crisis, the volcanoes and fault lines of the world would continue doing what they do, while the instruments watching them went dark. The sun does not negotiate. It does not consult our infrastructure planning timelines. It does not wait for grid hardening projects to be funded and completed. The U.S. government has not allocated the funding to install the massive surge protectors, essentially enormous electrical buffers placed at key transformer nodes, that solar storm expert John Kappenman at Oak Ridge National Laboratory estimated could provide meaningful protection for approximately $1 billion. $1 billion against a potential $2 trillion catastrophe. The math of that comparison should be one of the most urgently discussed numbers in the entirety of modern risk management. It is not. The NOAA Space Weather Prediction Center issues forecasts 24 hours a day. The ACE and DSCO-VR spacecraft at L1 measure solar wind conditions in real time. The warning system exists. The detection capability exists. What the research confirms is that significant gaps remain in warning lead time, in grid protection hardware, in satellite hardening, in the international coordination required to protect a globally interconnected system, and that these gaps are known, documented, and not yet fully closed. Monitoring is in place and detection is possible, but the margin of warning for the most critical variable remains 15 to 30 minutes. On July 23, 2012, a Carrington-class coronal mass ejection, measured by the AC spacecraft as it passed through the L1 point, narrowly missed Earth by approximately 9 days. It was moving at 2,250 kilometers per second. Had it been directed at Earth, had the geometry of the solar disk been rotated 9 days differently, it would have struck. Scientists who analyzed the event confirmed it met the criteria for a Carrington-class or stronger storm. It passed through the space where Earth would have been 9 days earlier or 9 days later. The margin between the civilization-altering event and the near miss was the rotation of the solar disk. 9 days. The orbit of Earth through its own path around the Sun. That is the gap between what happened on July 23, 2012, and what could have happened. That July, no one outside the space weather community noticed. The auroras did not appear over Reykjavik. The grid did not collapse. The satellites stayed in orbit. The dialysis patients received their sessions. The insulin stayed cold. The lights stayed on. Solar cycle 25 is past its confirmed peak, but the peak sunspot count does not define when the most dangerous individual events occur. The 2003 Halloween storms, some of the most powerful ever recorded, with flares measured at X17 and X28 magnitude, and X-ray detectors pushed off scale, occurred during the declining phase of solar cycle 23. The 1972 storm, which exploded magnetic sea mines off the coast of Vietnam and posed extraordinary radiation risk to the Apollo astronauts flying between missions, occurred in a declining cycle phase. The February 2026 X8.3 eruption occurred in what should by solar cycle mathematics be a quieting sun. The sun does not read the mathematics. The sun produces what the magnetic complexity of its active regions demands, and it produces it on timescales that our warning systems measure in minutes. What the sky is burning green means, the auroras that appear during intense geomagnetic storms, the green from oxygen at 100 kilometers altitude, the red from oxygen at 200 kilometers, the blue and purple from nitrogen, is that Earth's magnetic field is being compressed and distorted by an incoming wall of solar plasma. The auroras are beautiful. They are also the visible signature of geomagnetically induced currents building in the ground beneath them, flowing through pipelines and power lines and buried cables, searching for the path of least resistance, finding the transformer windings of the high-voltage grid. They are the light show announcing the arrival of something that moves at 1.5 million kilometers per hour and carries more energy than the combined explosive output of every nuclear weapon ever built. They are the notification that the 15-minute clock has started. Whether it ends with a story about unusual auroras visible from unusually low latitudes, or whether it ends with what the National Academy of Sciences described in precise bureaucratic language as extensive social and economic disruptions lasting 4 to 10 years, that depends entirely on one number, one measurement, the B's component of the interplanetary magnetic field. And that number is unknown until the wall of plasma is 15 minutes away. The sun has done this before, not in a mythological past, not in deep geological time. In 1859, in 1921, in 1972, in 1989, in 2003, in July 2012 when it missed. And in February 2026 when the largest sunspot of this solar cycle erupted with an X8.3 flare and the CME arrived with northward BZ and the world continued as if nothing had happened. Because nothing did. That time. The green light in the sky is not the danger. The green light in the sky is the warning that the danger has arrived. By the time the sky turns green above your city, the decision that determines what happens next has already been made by a number measured 150 million kilometers away, 8 minutes before the light arrives, and confirmed 15 minutes before the wall arrives, and the wall does not turn around.